Have you ever just stopped and thought about the invisible forces that power, well, everything? Today, we're going to pull back the curtain and decode the simple, fundamental rules that make all electricity tick. So let's dive right in. I mean, it really does feel like magic, right? You plug in your phone, it's dead, and then it just comes back to life. But what's actually happening inside that little charger? It's this perfectly controlled dance of energy. And the cool part is, it's all governed by a few really simple principles. Stick with me, and you'll see exactly what I'm talking about. All right, so to really get a grip on the language of electricity, we've got to meet the three main characters in this whole story. These are the invisible forces you'll find in literally every circuit out there. Doesn't matter if it's a tiny flashlight or a massive supercomputer. Okay, so how do we wrap our heads around something we can't even see? The best way, honestly, is to think about water flowing through pipes. It's a classic for a reason. So imagine this. Voltage, that's the water pressure. It's the push that gets everything moving. The current, that's the actual flow rate. You know, how much water is actually zipping through the pipe. And resistance? Well, that's like a narrow section of the pipe, something that's trying to slow that water down. So let's put some official names to these ideas. That push or pressure, that's voltage, and we measure it in volts. The flow itself, we call that current, measured in amps. And that thing slowing it down, the opposition, that's resistance, and its unit is ohms. These three are the stars of the show, and they're always interacting in a circle. Okay, so we've met the players. Now it's time for the rule book. There's one single, incredibly important rule that explains how they all work together. It's basically the grammar of electronics, and it's called Ohm's Law. This was the big aha moment for Georg Ohm, and put simply, all it really means is this. If you crank up the pressure, the voltage, you're going to get more flow, or more current. That is, as long as the pipe doesn't get any narrower, right? As long as the resistance stays the same. It's this super elegant, totally predictable relationship. And you can boil that whole idea down to one simple, beautiful equation. V equals I times R. Voltage equals current times resistance. I'm telling you, this little formula is the absolute bedrock of all circuit analysis. It's so simple, but it is so powerful. And hey, here's a great little trick to remember it, the Ohm's Law triangle. Just cover up the thing you want to find. So if you need to know the current, you cover the I, and what's left? V over R, voltage divided by resistance. Want to find voltage? Cover the V, and you've got I next to R, current times resistance. It's the perfect little visual cheat sheet. So why does any of this matter? What's the big deal? Well, this one simple law is what lets us control electricity. It's how engineers can design a circuit and know exactly how it's going to behave. They can predict precisely how much current is going to flow, which means our gadgets work the way they're supposed to and they don't, blow up. It's what turns electricity from this wild, chaotic force into a predictable, useful tool. Okay, so we know how electricity moves. That's a huge piece of the puzzle. But that's only half the story, right? The real question is, how much work can that flow actually do? And for that, we need to bring in our final key player, electrical power. Power is all about how fast energy is being used up. You can think of it as the rate of doing work. So when you see how bright a light bulb is, or you feel the heat coming off your toaster, what you're actually experiencing is electrical power in action. And we measure that in watts. And guess what? Just like Ohm's law, power has its own super simple formula. It's just P equals V times I. Power is just the voltage multiplied by the current. So the amount of work getting done is literally the pressure times the flow rate. Simple as that. All right, now this is where things get really cool. We've got Ohm's law and we've got the power law. What do you think happens when we smash them together? We unlock this whole new level of understanding. This is where the magic happens. Okay, check this out. We start with our power formula, right? P equals V times I. But wait, we also know from Ohm's law that V is the same thing as I times R. So what if we just swap that in? We substitute the V in the power equation, do a tiny bit of math, and boom, we get a brand new formula. P equals I squared times R. Now you can figure out the power even if you have no idea what the voltage is. How cool is that? And we can do it the other way too. Let's go back to P equals V times I. This time, let's solve for current. From Ohm's law, we know I is just V divided by R. So let's plug that into the power formula. What do we get? Another awesome new tool. P equals V squared divided by R. Now we can find the power without even knowing the current. And there you have it.
The whole shebang all in one place. The ultimate cheat sheet for basic electronics. Look at this. As long as you know any two of these values, say voltage and resistance, you now have a formula to find everything else. This is the complete toolkit. It's everything you need.
Okay, theory is great, but how does this stuff actually apply to the little components you use in the real world? This is where it all stops being just numbers on a page and becomes absolutely critical for making things that work and, maybe more importantly, things that don't go up in a puff of smoke.
So take a resistor, for example. Its whole job is to resist current. And when it does that, it gets hot. It's basically converting electrical energy into heat. But here's the thing. It can only handle so much heat before it just gives up. That absolute limit is its power rating. And yep, you guessed it, it's measured in watts.
You'll see these ratings all the time. A really common one for small resistors is 1/4 watt. Now, you have to understand that number isn't a suggestion. It's not a guideline. It is a hard physical limit. It is telling you the absolute maximum amount of power that little guy can handle before it literally cooks itself to death.
And what happens if you ignore that rating? It's pretty simple, actually. You get a puff of smoke and a sad, burnt-out component. If you push more power through something than it's designed to handle, it will fail. It'll just burn up. So you see, getting these power calculations right isn't just for a test. It's absolutely essential for building anything that works. So, I want to leave you with this. The next time you see a wattage rating, whether it's on a 60-watt light bulb or a 1200-watt microwave, you'll know it's not just some random number. It's telling a story. It's telling you exactly how much electrical work that appliance is doing, every single second. And it's all governed by those simple, elegant, and really powerful laws that we just decoded together.